So here we go. Problem 1 from homework 23. We're getting towards the end. So we have this spool that has a mass of 150 kilograms, and its inside radius is 0.2 meters. Its outside radius is 0.4 meters, and it's got a radius of gyration of 0.25 meters. It's on a slope of 30 degrees with a coefficient of friction of 0.1. And the spool starts from rest and then begins to slip. And it starts to move down the slope. So we want to neglect the fact that the cable is paying out and reducing the mass, right? So there's the cable's wrapped around there. We want to find the angular velocity and the linear velocity and the tension in the cable after it has gone after 4 seconds, right? And we want to use impulse momentum for that. Then we want to go and use kinematics to figure out what the acceleration is. And I think I accidentally wrote deceleration. I think I need to fix that. So I'll make sure I fix that before I post the problem. But it should be accelerating, right? Because it starts from rest and it starts moving, right? But we want to do that. We want to confirm that acceleration using Newton's second law, right? And then we want to confirm the distance that it has moved using work and energy. So this is an interesting problem. And so here I've written it out, set the thing up, and let's proceed with the first one. I think what I want to do first here is to get the moment of inertia. I'll get the mass moment of inertia. So I, about the center of the thing, is going to be mass times the radius of gyration. So we got 150, radius of gyration of 0.25 squared, and handy dandy Hewlett-Packard calculator, and 0.25 squared times, we get 9.375 kilogram meter squared. Other things I might want to do, I do want to have some type of relationship for kinematics. So it is slipping, so we have to be kind of careful right there. It is slipping and translating. I don't think we can necessarily make any kind of judgment about the kinematics here. So I think the best thing for me to do is to draw a impulse and momentum diagram. I'll make it a little smaller right here. And then to judge and see what's happening, right? So I don't know if I made those far enough apart. I probably didn't. So this makes for great video, doesn't it? Me watching me draw. I can't remember which side of the sides I used. I guess I put it over here. Okay. And there's nothing really happening on the first diagram, but it's a good idea to do this right here. So we got initial impulse and final. Okay, let's see, I'll draw the inner circle into the thing. Something like that right there, right? I didn't, I tried to make a dashed line quickly and just made a miss. So I guess I'll go a little slower, make less of a mess. But, you know, the act of this diagram has a couple different purposes. I mean, it represents what's taking place, but also makes us think, right? So we have to think about the loads. Okay, so there's nothing happening onto there, so we don't need to do anything. But we have a force, the normal force coming down. We also have the weight coming down, right? I should label this with a delta T next to it. And here's our tension, delta T. And here is our weight, delta T. Remember, these are all, and all these are going to be constant. Why? Because, well, there's no reason for them not to be constant. That's one aspect that you can think of. But I think they're all pretty well going to be constant. Now, here's one we have to decide on which way the friction is going to go. Is it going to be going up the slope or down the slope? Well, you know, if I had, let's see, I got to have something circular. How about the paper towel roll, right? So it's slipping, right? But the thing doesn't want to slip, so it has to be rotating this way, right? You can't really quite tell which way this is rotating. But here you go. It's got to rotate that way, right, to go down the hill. I mean, it wants to go. I mean, if it wasn't for the cord, it would be rotating that way, right? But the cord is stopping it from going that way, so it has to rotate this way. It's gonna pay out as it's doing it, the thing too, right? So it has to pay out. So it's got a rotation coming this way. So it would be making a force that way down the slope. Therefore, the force has to be up, right? The force can be going upwards onto the thing. So it has to have a force that direction. I think I'm correct in that, yeah. So I have a friction force, and that's going to be times delta t, because remember, these are impulse things. And we want to take a coordinate system probably that's aligned with that's going to help us. And if we were taking a look right here, this way here, that angle would be theta. When it's done, it will, after that delta t, it's going to have a velocity. So it's going to have a mass times v2, right, from the center of mass. But it's also going to be rotating, let's see, it has to be rotating clockwise, right? It has to be rotating this way with its moment of inertia times the angular velocity. It just has to. It doesn't have any choice because of the way that the cable is arranged. Let's see, anything else I want to do here? I don't think so. So what we're really going to do is we're going to set up some equations. The first one I might want to do, and I've seen where some solutions to problems like this, they use the impulse and momentum in the y direction in lieu of doing an FBD. So we could do that actually. So we can in the y direction, because that's just as true as anything else. I mean, its initial velocity is in the y direction is 0, and maybe I should write out the main equations underneath this right here. We could go so the system. This is the main concept. System momenta, plural of momentum at state 1, plus the impulse from 1 to 2 is going to be equal to the system momenta 2, right? That's what that diagram represents. So the translational in the y direction of that is going to be 0, and we're talking y prime direction, right? So we're talking about this. We're going to get the negative weight times delta t, right? Times, and that's the way down that way, but now we're going to go times the cosine of theta, and then plus Fn delta t, and then there's nothing else going on here, and that's going to be equal to 0, right? So what we're left with is that Fn is going to be weight times the cosine of theta, because the delta t's cancel out. So that's just going to be mg cosine of theta, or the mass of the thing is 150, 9.81, and cosine of 30. And so we're left with 150, 9.81, and oops, I meant to multiply those, and 30 cosine times. So 1,000 274. And these are newtons. Let me double check that. I don't like... yeah, I did something wrong. 150, 9.81 times. All right, no, that's fine. Okay. And 30 cosine times. Okay, I got that. All right. So the friction force is just going to be 0.1 times that. Don't have to do that in my head, right? 127.4 newtons. Duh. All right, so now we're going to do in the x prime direction. And we start out with 0. And we're going to have positive Ft times delta T. We don't know Ft, the tension force. And then we're going to have minus W delta T times the sine of theta, right? And then plus friction force times delta T. And we do know this. So here's an unknown here. And then that's all there is, an impulse, and it's going to be equal to, and we say that's going to be negative mv2. Right, so that's linear momentum. And let's put in the stuff that we know, I guess. Sure, we know that it's 4 seconds minus mg, or 150 times 9.81, and then delta T is 4, and sine of 30, plus friction force, 127.4, 4 seconds, equals negative 150 V2. Right, so we have, let's collect all of these things. And sometimes I will maybe solve for the tension, because I'm kind of recognize I'm going to try to get rid of that in a minute and put it back into there so I can isolate my velocity onto the thing. So Ft is going to be equal to, so everything else is going to go over to the other side. So we have 127 times 4, and then 159.81 times, okay, 4 times 30 sine times, right? And I'm going to subtract that from that. All right, we get a negative number, but it's going to come over to the other side. And I'm going to divide by 4. So I get 608.3. And then minus, but I have to divide that 150 by 4, right? Which would come out to 37.5 V2. And I'll call that equation 1. Now I need to also apply the impulse momentum for the angular stuff, right? And I want to take it about the this point right there would be good. Let me see. Or actually, let me think here. I could do it about the center of gravity. That's actually that's a good trick. Because now I don't have to include that velocity right here. But I do need to have something that connects the two things. Oh, well, the instantaneous center of rotation will make it so that the velocity, yeah, so we'll be able to connect right there. So I should have done some kinematics. So even though it is, oh man, I don't like that. Oh boy. Ooh, one second. Let me think about something. I want to stop. All right, so sometimes you gotta keep learning, right? Don't always know everything all the time. But here you go. All right, so in this piece right here, with our kinematics, instead of being the ICR being here, because it's slipping, the ICR is actually right there because that's where the cable goes, right? So this is the ICR. So when this thing has a velocity that's coming down this way right here, this is the actual thing, the omega, if this is the velocity of the center of the thing, right? So we can write out that the velocity is equal to omega Ri, because that's the distance, right? Because so this point right here, because on the cable at any given moment it's going to be, it's not going to move, right? You just like anywhere along that cable after the fact, after it's paid out, it's like, that's zero. So at that center right here, the relative motion between the wheel and that piece, it's just like being on the road, except it's the cable. So that's an interesting little twist that we've placed onto this thing. Not something that I necessarily saw right away, but it's good. It's good. We're recording now, right? Yeah, we're recording. I don't know. I couldn't remember if I started the thing up. So that's going to help us. All right. So let's see. I'm still doing the system momentum here. So we go angular. Maybe angular momentum. Angular momentum. So we did about the x, and we did about the y prime, we did about the x prime, now we did about the angle. It's going to start out with 0. There's no I omega going on here. I should say about, and actually maybe I should write out the equation for this. So we go I omega 1 plus, I think it should be the integral of the moments dt, and I haven't said what it's about yet. It's going to be equal to I omega 2. And it's, if we do it about the center right there, we don't have to include any of the effective ones, right? So if we did it about like down here, for instance, we would have to have that velocity, because that mass time, or this one over here, the mass times velocity is momentum, and it's going about a point, and therefore we would have to do this. But we can go ahead, if we do it about the center, that works everything out. So we start out with 0 right here, and then we start, we make the counterclockwise as positive. So we see that this one is going clockwise, right? So it's going to be a negative ft times delta t, and that's going to be times ri. The weight doesn't do anything because it's going right through the center right here. The normal force doesn't do anything because it's going through the center that we're taking the thing about. But the friction force is going to do something. It's going to go positive because it's going clockwise, and it's going to be friction force times time, but then times the distance too, right? So that's going to be RO. Hopefully this works out. And then we get over here, and it's going to be equal to, it's going to be a negative I, and then omega 2. So we know a lot of the things in here, right? So we're going to have a negative ft. We don't know that. But we do know that it's 4 seconds. And then the RI, the inside radius, is 0.2. And then the friction force, we found that somewhere, was 127.4. 4 seconds have elapsed, and the outside radius is 0.4. I have to be careful with my values. I might have to redo this whole thing if I find that my values don't make it so that thing doesn't actually slide. That's a hazard when modifying problems, and I do that a lot. Should have checked it maybe, but I think we're going to be okay. I think, yeah. And minus, and the mass moment of inertia was 9.375, and we don't know omega 2. So I could solve this for my tension, because I'm going to equate them here in a second. And so let me see. I'll take this value. I'm going to be careful with my signs on this. So I'm going to go 127.4 times 4 times 0.4. All right, so that's 203.8. And I need to divide by 4 and divide by 0.2. So I get 254.8 right here. And that's going to go, so this will be a positive number, 254.8. And then this is going to come over to this side, and that's going to come over to this side, so it's going to be a positive. And I need to divide 9.375 by 4 and 0.2. Ooh, 9.375. I think I left out the decimal place. 0.2 divide 4 divide. Yes, I did. I'll get 11.72 omega 2. All right, so this is going to be my second equation. I still have, now I need to relate, with these two, I need to relate what my omega 2 and my V2 is. So like I kind of jumped the gun. I kind of saw that coming. So that's when I went over here and I said, And I might have to sit here scratching my head a little bit and trying some things before I finally come to the conclusion that my ICR is right there. But that's my other equation right there. I didn't do a good job of organizing this right here. I could say that the velocity is equal to R I omega and call that equation 3, right? So 1, 2, and 3 together. So let's take 1, which was what happened here? Something's making my paper dirty. That's not good. So 608.3 minus, let's go for velocity first. So we'll 37.5 V2 is equal to 254.8 plus 11.72, and maybe we could say that omega is equal to V over Ri, which is going to be V over 0.2, right? V2 over 0.2. And hopefully we get a positive number, right? Because we already established the direction of the velocity with this is going down the hill. So one must hope that we get the right directions in here. So, okay, so we can subtract out here. And that's going to add over there. Okay, so I think, yes, we are going to get a positive value. That's good news. So we get 608.3, subtract out 254.8. Boom. And now we're going to add 11.72 divided by 0.2. All right, so that's 58.6. Add it with 37.5 plus, and then divide. And we get 3.678. These are meters per second. So we're doing pretty well. And now we want to find the angular velocity. So we can get the angular velocity is going to be v2 over 0.2. So 3.678 divided by 0.2. And that becomes 18.39 radians per second. And now let's find the tension. We could do that with either equation 1 or 2, but let's find it with equation 1. 608.3 minus 37.5, 0 in there, 18.39. Boy, I hope that comes out. 37.5 times that. Ooh, that's not good. Can't push a rope. I must have made a math error, so let me pause and find my math error. Oh, okay, I got it. All right, I don't know what I was thinking. I needed to put I didn't put the 18.37 in there. I put the 3.678 in here. Jeez, that was dumb. All right, so that's not so bad. So 608.3, 37.5 times my 3.678. Subtract it out. Great. 470.4 newtons. We could try it out into here to double check if we wanted to, right? So we could say that 11.72 times 18.39, and we add to it 254.8. Yes, and we get the 470.3. Yeah, so we got that. Okay, good. So we did the first part. And I know that makes this for a pretty long problem, but it's important, I think, to, so it's already 27 minutes, so it's gonna be a long problem. But we did the next part of the thing to, we want to find the acceleration and the delta S. And we could do that because we have time. Right, so we're using kinematics. And everything's constant. All the forces are constant, so we can expect a constant acceleration. And so for the distance that we're moving here, for the distances, let me see if I can think of that correctly here. The distance in the delta x along here is going to be equal to this delta x prime, by the way, the initial velocity in the x direction, but everything's in the x prime direction, times time, plus 1/2 acceleration times time squared. I think so. Okay. So we don't have the distance. Darn. But what we could do is we have initial velocity. No, we have final velocity. We have the final velocity. That's what we have to do. Sorry. We have the initial velocity squared plus 2 times. No, we don't have that. Let me think about something. No, all we have to do, we have to do the simplest thing. Velocity is equal to initial velocity plus acceleration times time, right? So we can find what the acceleration is going to be equal, because this is 0, is just velocity divided by time. So that's just 3.678. I mean, that's obvious as can be. I don't know what's going on with me, but that's all right. So let's take 3.678 and divide it by 4, and we get a 0.9195 meters per second squared, right? And now we can find the position. We could either use this to find the position, or we could use the other one that I wrote down. But this is probably going to be easier, right? So the delta, and so this will be delta S, which is the delta X right there. And that's going to be equal to initial velocity times time plus 1/2 acceleration times time squared. But that starts out at 0, so all we need is 1/2 acceleration 0.9195 times time squared, or 4 squared. So 16 times that divided by 2. And so we say it was going to go down by 7.356 meters, right? So now we want to do the hard work of part C, find the acceleration. Here's one that I'm a little concerned about because of the angular acceleration. I think I'm going to be okay. So, so what we want to do here, maybe we want to solve for what the tension is going to be. Maybe that's the way to go. What we want to do is want to work back. We want to pick something from that we can find, and I don't know if I can find the angular acceleration from this right here. We could set them equal to each other. So things we don't know, we're going to pretend like we don't know the tension force, but we do know this acceleration. Let me see the way that I phrased the problem here. Confirm the acceleration in part B, right? So okay, so we want to take the tension, right, that we want to as part of this. Yeah, let me see. I didn't solve this one yet, so let me think about this. I was able to confirm these things, but I'm going to change the problem to simply be answered with what we've done, because it's already, the problem's too long, and I didn't want to make a really long problem. I thought it would go a lot faster, so that's the thing. So I'll modify the problem, so we'll only be asking for that part A, really, for the thing. So for the answers, will be what did I ask for? I wanted omega. So omega is 18.4 radians per second, and it is going clockwise. So, and then the velocity, and look, that's omega 2, and velocity 2 is going to be 3.68 meters per second, and it's coming down that way 30 degrees. And then the tension is 470 newtons in tension. I thought I would make something clever that would be very informative, but I think it's just going to take too long to do. So I am just going to make this into a shorter problem. But of course, for those who are watching videos and not doing the problems themselves, it'll still take about a half hour to do, or whatever it takes to transcribe this. So there you go.